دكتور بس سؤال. اي هتنزليه على يوتيوب؟
Yeah, sure, I will. Okay. So in problem 1, we have a solar collector of efficiency equals to 85%. Whenever they gave us the efficiency, it's equal to the useful power, if you want, over the provided power. So this is equal to the useful power. In our application here, we want to heat water. So the useful power, it will be just calculated from calculation of heat absorbed by water. Or if you want, of course, and we convert it, the unit should be the same. And if we talk about power, the unit is watt. So the useful heating power can be calculated using which formula? How can I calculate the useful power? What is my application here? I have a solar collector, okay? The solar collector will absorb solar energy. And
Professor, we take the power, we do energy conservation. We take the power of the solar collector, we
yes,
equate it to m dot
yes,
H out minus
exactly.
Xn, which is Cp delta T,
Exactly.
temperature.
Okay, so we should divide the useful power over the extracted power from the solar system. Okay, over the extracted power. So first, to know what is the value of the extracted power, we have, of course, they should give us the absorptivity of the solar panels and the flux, the heat flux that is coming, the solar flux coming through the panels. So this is why they told us that they gave us the following properties for the solar panels. First, we know that the total area of our panels is equal to 15 meters square. We know that the solar intensity that is incident on our solar panel is I equal. So if you remember, you just need a basic knowledge from the conservation of energy chapters, okay? And you don't have them, but just you should understand the concept to be able to apply it in simple applications. So if you have the solar intensity that is incident on solar panels is equal to 400 watt per meter square, and you already know that you have a certain property that is the absorption that will tell you how much will get in your panel, and the remaining part will be reflected. Okay, so this is why they should give us the absorption coefficient. And if they don't give you this coefficient, you can consider that the absorptivity is the alpha is equal to 1. Okay, but if they give you alpha, then you should multiply I by alpha to get what is the proportion absorbed. Here they said that the area is 15 meters square, the intensity is 400 watt per meter square, and is used for domestic water heating. If they don't, as we mentioned, if they don't give the value of alpha, we consider it a perfect absorber, okay, and we take alpha 1. So since we don't have any information here, and we should, to be able to continue our problem, we can do the assumption of perfect absorber and put alpha equal to 1. In general, for a shower, minimum we should heat water up to 70 degrees in order to kill bacteria. Okay, so T heating should be larger or equal to 70 degrees. So when we do the design, we should make sure that the mass flow rate circulating in the solar panel will provide us this temperature. If not, we should do some redesign of our system, okay, in order to reach this temperature. In this problem, we know that the initial temperature of water, T initial, is equal to 25 degrees. And we know that the mass flow rate passing through the system, m dot, is equal to 0.025 degrees. 0.025 kilogram per second. And what we want to determine is the temperature of water at the exit. So we know the inlet temperature, Tn. We need to calculate the value of Tout, okay? To make sure if we are able to reach the required temperature, which should be larger or equal to 70 degrees, okay? So now all we have to do is to do a small energy balance. So you have water coming in and out, and it's absorbing energy through the solar panels. So from energy balance, we can write the following. We can write that Q absorbed, Q dot absorbed, Q dot, Y dot, because we have the values in watt, energy per unit time. So Q dot absorbed equals to M dot. It is right what I did. No, Q dot absorbed is equal to M dot Cp delta T.
Yes,
What is Q dot absorbed?
it's the power from the solar panel.
Okay, and how we calculate it? What is the value of this power?
It's the area times the irradiance.
If I do the area times the irradiance, I find what? How do I use then the
Find the
efficiency? Why they
power
gave
to
me
this
the
max
efficiency?
power. You need to
Hmm?
multiply the efficiency.
Yes. So please don't forget to multiply by the efficiency, because A times I will represent the extracted power from the solar panels. Okay, and the solar panels will extract from the sun this amount of power, which is the area times the intensity, and the unit will be in watt. Okay, but actually, because of you have several reasons that will cause a certain reduction of this heat transfer to the water. Okay, this is why we talk about a certain efficiency. Okay, and in case they gave you the value of alpha, you should first do alpha times A times I, which will give you the extracted power, and then you should multiply by the efficiency, which is epsilon, which is 85%. Okay, you know that many of you have already taken heat transfer courses. Any heat exchanger, and this is very similar to a heat exchanger, because you have if you want the flow of water and it's in contact, it's taking heat from the solar panel, so it's like a heat exchanger. And any heat exchanger is characterized by a certain efficiency. It cannot transfer energy if you want without any loss. That's why we have to multiply alpha AI by epsilon to get what? To get the useful power. So here the useful power will be Q dot absorbed by water is equal to epsilon times alpha times A times the intensity, equals to, of course, it's m dot Cp delta T. M dot represents the mass flow rate of water. Cp is the specific heat of water. And delta T is T out minus Tn. So delta T will represent T out minus Tn. In this equation, you have everything except the inlet temperature. Okay, that's why when you replace, you will get your unknown, which is T out. And please pay attention for units. Okay, as we mentioned, Q dot after multiplying by the area, you will have Q dot in watt. M dot should be in kilogram per second. In general, Cp, you should know Cp for water, and just know for this exam the characteristics of water and air. If we have any other fluid, I will give you the characteristics. But for water and air, because we use them a lot, you should be familiar with their values. Okay, so for water, you can use 4.2 kilojoule per kilogram Kelvin. Since if you used Q dot in watt, you should convert to joule. You multiply by 10 to the power 3. So it's 4,200 joule per kilogram Kelvin. And you have delta T Also for delta T, pay attention, the two temperatures or both should be in degrees or both should be in Kelvin, because as you know from heat transfer, it doesn't matter if we do delta T both in degrees or both in Kelvin, because temperature in Kelvin is temperature in degrees plus 273. So if you keep Tn in degrees, you will get T out in degrees. And once you get T out here, you should be able to know if the design is fine or not. If you get T out smaller than 70 degrees, you say, I should redesign my system because I'm not reaching the temperature required. Okay, and for example, if you get T out smaller than 70 degrees, what are the strategies that you can do in order to reach the temperature that you want? What can you do then? If you didn't install yet your system, you are doing the design, okay? You should try to, in order to increase the value of T out, you have several possibilities. One, okay, you can decrease the mass flow rate. You should, but in this way, you should wait more time to do your shower, because you need to decrease the mass flow rate to increase delta T, but this will require a longer time to heat your water. This is a first strategy. A second strategy is, if you didn't install yet your system, you can try to increase the area of your solar panels. So you should install more solar panels. So in general, whenever we design a system, we say we don't want to wait 2 hours, let's say, for water to reach the hot temperature. Let's say we consider, for example, a good time maybe to be 1 hour. We say the time, okay, should be just 1 hour. So we have a certain volume to heat, a certain mass of water to heat. Once we determine the time needed, we can consider then what should be the value, if you want, of knowing delta T, we find the value of m dot, and then based on this, we specify the design required. Sometimes we fix m dot and we say what should be the area, or in other cases, we have a restriction with the area, and we don't have a lot of space, so the area might be imposed, then we can play with the mass flow rate. But again, time also is important, and it depends on the problem. This problem can be asked in several ways. They can tell you we are restricted with this area, what can be the minimum mass flow rate m dot to use, okay? Or,
Professor,
yes?
so if we're restricted by time,
Yeah.
اللي بيصير
For
إنه
restricted by
then
time. Okay, what should we
instead
do?
of yeah,
If we
instead
say,
of
for example, you have a certain volume, okay? You want to heat it, in a certain time. What do? You have the volume, you multiply by rho, you get the mass, okay? You get the mass, and you have a restriction on time, and you need to heat this mass during this amount of time. So now you can calculate m dot. What should be m dot? M dot is simply the mass that you want to heat to this temperature over delta T. Okay, so you can calculate what is the mass flow rate that you should circulate in order to heat during this period. Now, for this mass flow rate, you should ensure that delta T is high enough. Okay, if you find that using this mass flow rate, you cannot reach 70 degrees with the area that you are constrained with, then you don't have any choice. You should increase the time. Okay.
So
Yeah.
Professor هون انه انا I'd impose my delta T to make it 70 يعني 25 minus 70 تقريبا 45. So بصير عندي delta T is 45 و m over I look for m dot in this case.
Yes, this will give you, if you want, the maximum possible m dot. Okay, لأنه for a certain, if you increase, if delta T is larger, m dot will be smaller. And if you just want to heat to 70 degrees, okay, you can get the minimum mass flow rate that you can, the maximum mass flow rate that you should circulate. Okay, and if you increase more the mass flow rate, then delta T will be reduced and you will not reach your temperature. Why it's good to increase the mass flow rate? Because you reduce the time, and you reduce the time of heating.
Exactly.
Okay, so here you have, it depends on the constraints you have. If you have, let's say, as we mentioned, a minimum temperature to reach, which is 70 degrees, you say I can calculate the corresponding maximum flow rate, and based on the area I have. And in case I impose delta T, and I impose the time, and I impose delta T, then I should play with the area, and I should redesign my system if I have flexibility with the area. Any other question on this? Okay, so this is for the first problem. Let us move to the second one. In problem 2, it's an economical analysis problem. So we have the lifetime of a 2 kilowatt wind turbine. So we have a 2 kilowatt wind turbine. Has a lifetime of 30 years. The initial capital cost, I, is equal to 1,500 euros per kilowatt. And we need a yearly maintenance cost equal to 75 euros. And the operational costs of 50 euros. Now, the salvage value is equal to 450 euros. And the turbine operates for the number of hours of operations is equal to 2,800 hours per year. Now, the selling price of the generated electricity is 0.09 euros per kilowatt hour. First, knowing that the discount rate is 3%, we should calculate the capital enrichment rate, CER. Okay, so first, whenever they ask for the CER, please pay attention. You always calculate the CER at the end of lifetime. So by definition, the CER is equal to the net present value of a certain project at the end of lifetime, and this corresponds here to n equals to 30 years, over the investment, which is equal here to, how to calculate the investment? We have the investment is 1,500 euros per kilowatt, and our wind turbine is 2 kilowatts. So all we have to do is to multiply by 2. So I is equal to 2 times 1,500. Now, we still have to calculate what is the NPV at year 30. Okay, so whenever we want to calculate the NPV, we should determine over the whole lifetime the costs and incomes of our projects. Okay, so let us now write what is the NPV. So first, we know that the net present value, okay, represent the value of incomes and costs all back to present. Why we do this? Because we know that with time, the value of money will not remain the same, okay? Because of a lot of factors that we discussed in the course material. So that's why we first, all costs and investments are counted as negative, and all incomes will be counted as positive. So of course, for the investment is minus I. Now, if we put the general formula, it's a plus summation for I going from 1 to n. And here, since we want to calculate the NPV at the end of lifetime, so we should put until 30 of the revenue at each year I minus the cost for each year I over one plus A. And this term over 1 plus A to the power I is to take into account the discounted value of money with time. Okay, don't forget that only when you calculate the CER or when you calculate the NPV at year N, you should add what we call the salvage value, because it represents, if you want to sell your system at the end of lifetime, you can sell it with a certain amount of money. And this amount is the salvage value which is given. But because you are selling it after a long period of time at the end of lifetime, you should not forget to discount its value, and this is done by dividing it by 1 plus A to the power n. Okay, so this is the salvage value. Now, in this problem, they gave us A. A is 3%. Please pay attention. A, you represent it by 0.03, and you don't put 3. It's 0. You divide 3 by 100. So A is 0.03. The investment, we already calculated its value, which is 3,000. Now, concerning the salvage value, it's given to be 450. So just we have to replace it by 450. Now, this summation is challenging in general when we have variation of the income and costs. But it's not the case, and we already have done a detailed problem about this. What can we do when we have variation of incomes or costs with time? But since in this problem, it's not the case, so it's relatively simple. Since the incomes and costs are are constants, so we can take them outside of the summations. And we can write that RI represent, if you want, the incomes that we can get from selling the electricity. And it's equal to the number of kilowatt hour produced, okay, to calculate times the price per kilowatt hour, okay? So we need to multiply the number of kilowatt hour produced by our turbine times the price per kilowatt hour. So it's equal. Now, concerning the number of kilowatt hours, they told us that we have the number of operation per year of this turbine is 2,800 hours. Okay. Just pay attention for units. You have, this is the number of operation, number of hours. Okay. And since the unit here we have the price per kilowatt hour. So we should multiply by the number of kilowatt hour. So now we should multiply the number of operation by the power of turbine in kilowatt. So in case you have the power in watt, don't forget to convert to kilowatt. Already here, we have it in kilowatt. It's 2 kilowatt turbine. So we just have to multiply by 2 times the price per kilowatt hour, which is 0.09. Okay, so now we have the value of our RI. Now concerning the cost, CI, we should add the operational and maintenance cost. And here, as we mentioned, they are constant. So we just find CI one time. So we have a cost of 75 euros for maintenance. We should add to it 50 euros for operational costs. So we get in total 125. Euros. Okay. Now, once we do this, then all we have to do is to replace in our equation. Look, you can use in the exam, of course, I will give you the geometric summation. And you don't have to memorize it, just you can use it here. I will give you in the test what is summation from 1 to n of 1 over 1 plus a to the power I, and you can use this formula to get the NPV. Okay. So just you have to do a replacement here and you get the value of NPV. And once we get NPV at year 30, we can verify if the project is profitable or not, because once we get NPV at year end, we can calculate the CER. And as we mentioned in the course material, for the project to be profitable, the CER should be larger than 30%. Okay, if you get a CER lower than 30%, then you say we don't advise to continue with this project, or we can try to redesign or proposing some recommendations in order to enhance the profitability of this project. For example, here, if I tell you, if you have a CER smaller than 30%, and I ask you, what can you recommend to increase your CER? What can be your strategies? What can we do? If you just look at the formula, you can know what we can do. First, we can try to reduce the investment, and we can try to buy another wind turbine. And of course, we should compromise between the specifications and the price, and we try to get a good turbine with a lower price. Plus, in this term here, we can try to increase the selling price, and instead of selling the kilowatt hour at 0.09, of course, we should still be competitive in the market, and we can play with a certain range of selling prices. Or also, we can increase the number of operation, but we should make sure that this will not be bad for our turbine. Another strategy also might be to try to reduce the operational and maintenance cost. So we have a lot of strategies that we can tackle in order to enhance the CER. And if we are not able to do these strategies, we stop. We say, this project is not profitable. Let us look for another alternative. Okay. So this is for the first question. Now, the second question is to calculate the non-discounted payback period. Who can tell me, what do you understand by non-discounted payback period?
A equals 0.
Okay, A equals 0. This is if you want, but if you replace A by 0, Fadi, if you replace it by 0 in the formula of the geometrical series, you get an indeterminate number. So whenever you have A equals 0, you cannot use this formula of summation, but you should go back to the concept. Okay, if A is 0, this means what? Do we have any discounted value for money with time?
No.
No, as the name indicates, it's a non-discounted payback period, and we consider that the value of money will remain the same. And this will simplify a lot the calculations. You know why? Because now when we calculate the NPV, okay, let us write it again together without the variation of value of money with time. So we have minus I plus summation from 1 to any year n. Here, when I want to calculate the payback period, do I include the salvage value?
No.
No, because the payback period will be, hopefully, أكيد, will be before the end of lifetime. If you get n larger than the end of lifetime, this means that you will never get a NPV equals 0, and then your project, of course, is not profitable. So whenever we calculate the payback period, we don't include the salvage value because we assume that n is smaller than the n, big N. So now, no need to put over 1 plus a to the power I because we don't have any discounted value, okay? And then this is the formula. And if you want to get the year, because here the income and costs are constant over the years, then you can write simply that NPV is minus I plus N, which is the number of years, times R minus C. Okay, we have already calculated per year what is the income, and we know what is the cost. We have the investment, and the payback period correspond to NPV equal to 0. So now you can say that N is equal to R, to I over R minus C. This is because here, this is constant. If it was varying with year, all you have to do is to decompose this term, okay? But the concept is the same. So N is I over R minus C. And then you can get the value of your payback period. And from here, depending on this value, okay, you can see what is the time needed to get your money back. But can you tell me, is this value very representative? And if you calculate the non-discounted payback period, it is enough? What is the disadvantage of taking A0?
Professor, is NPV necessarily 0?
When you want to calculate the payback period, yes. Okay, the question here is to calculate the non-discounted payback period. What is the meaning of a payback period? Payback, as the name indicates, and it's the time when the incomes will just be equal to the investment and cost. Okay, so whenever they ask you about a payback period, you should put NPV equal to 0. If it's a non-discounted payback period, and you don't take into consideration the discount of the value of money with time, you put A0. But in general, we care for the discounted payback period. We put a value for A. And in this problem, for example, if I ask you now to calculate the discounted payback period, and I gave you that A is 3%, you will go to the previous relation and set NPV equals 0, and you add here summation from 1 to n of Ri minus Ci over 1 plus A to the power I. And here,
You still don't account for salvage.
نعم.
You don't account for salvage كمان هلا.
No, you don't account for salvage, of course. لأنه الpayback period, you assume, Fadi, that it's smaller than the total lifetime. If you get, as a result, a value larger than 30 years, then you say my assumption was wrong, and I will never pay back, my system will never pay back money that I put. Okay?
Deal, thank you.
Any other question on this?
بس كمان الجيومتريك سيريز هون what would you use? It's one over
Geometric series here is a Fadi, if you did the problems I posted for you before, you have a formula that will give you directly what is summation.
It's 1 over 1 plus A
Yeah, exactly. You use it. You can use it directly. But if A is 0, you cannot use this summation لأنه
لا.
بتصير ال A
لا.
تحت, okay, بالdenominator.
Exactly.
Okay.
Thank you.
The last question in this problem is to calculate the ROI value. What is the ROI? It's the rate of return on investment. Okay. What do we mean by ROI? We mean it's the value, if you want, of the
NPV.
discount rate for which the NPV will be 0 at the end of lifetime. Why we calculate the ROI and what is the significance of the ROI?